In today's video, we will be exploring some of the most iconic bridges around the world. Bridges are more than mere structures made of steel and concrete. They are lifelines that connect people, cities, and cultures. Let's dive in. 1. The Golden Gate Bridge is an iconic symbol of San Francisco and a testament to American engineering prowess. It took 4 years to construct and was completed in 1937. It spans 1.7 miles across the Golden Gate Strait and connects San Francisco to Marin County. Designed by engineer Joseph Strauss, with significant contributions from architect Irving Morrow and structural engineer Leon Moisseiff, at the time of its completion, the bridge was both the longest and tallest suspension bridge in the world. It had a main span of 4,200 feet and its towers reached 746 feet above the water. The bridge had both a distinctive orange color and Art Deco style. The construction of the bridge marked significant advancements in engineering. Like all projects that push the boundaries of construction and engineering, the Golden Gate Bridge faced numerous challenges, including strong tides, frequent fog, and the Great Depression. Today, it stands as a testament to human ingenuity and resilience, attracting millions of tourists annually and symbolizing the pioneering spirit of the United States. Construction of the Golden Gate Bridge featured several engineering innovations that were groundbreaking for its time. The suspension bridge design element required the use of advanced calculations and materials to ensure stability and strength. The towers of the bridge were constructed with a flexible yet robust steel framework to withstand high winds and seismic activity, a pioneering approach to earthquake engineering. Another major innovation was the implementation of a movable safety net underneath the bridge during construction. This net saved the lives of 19 workers. Additionally, the use of high-strength steel cables, manufactured by Roebling's company, allowed for the necessary support and flexibility. Like all projects, challenges were faced during construction. The Golden Gate Strait has powerful tides and currents, which made anchoring the bridge's foundations extremely difficult. Workers had to contend with unpredictable water conditions while building the underwater supports. San Francisco's thick fog and high winds often reduced visibility, complicating the construction process, while high winds tested the stability and safety of the incomplete structure and the workers. Due to the construction of the bridge beginning in 1933, during the Great Depression, securing funding was a challenge. Despite this, the construction of the bridge provided jobs and thereby boosted the economy. The design of the bridge itself had to ensure stability against the strait's strong winds and potential earthquakes. Coordinating the construction of such a massive structure required precise logistics and scheduling. Transporting materials, managing a large workforce, and maintaining construction timelines were all complex tasks. 2. The next bridge we will explore is the Tower Bridge, an emblematic symbol of London, which was constructed between 1886 and 1894, during the height of the Victorian era, a period marked by industrial progress and architectural innovation. The bridge was conceived in response to the need to create a new bridge that would alleviate congestion without disrupting river traffic in the bustling area of London. Designed by architect Sir Horace Jones and engineer Sir John Wolfe Barry, the Tower Bridge embodies the distinctive Victorian Gothic architectural style evident in its pointed arches, detailed stonework and ornate appearance. The bridge was meant to harmonize and complement the historic surroundings. One of the bridge's most remarkable features is its bascule, also known as a drawbridge mechanism, which allows the roadway to split and lift, so that ships can pass through. At the time, it was a groundbreaking feat of engineering. The hydraulic systems that made this work was powered by steam at that time. It has since been updated to electricity. Tower Bridge's combination of aesthetic grandeur and mechanical ingenuity not only addressed a critical infrastructural need but also created an architectural icon. Today, it stands as a testament to Victorian engineering and remains one of the most recognizable landmarks in the world. Tower Bridge boasts several unique design features that set it apart as an architectural and engineering marvel. The bridge's iconic twin towers, constructed in the Victorian Gothic style, are both functional and decorative. These towers house the machinery for the bascules and provide structural support for the suspension elements of the bridge. The design, featuring pointed arches and detailed stonework, ensures that the bridge complements the nearby connecting the two towers are high-level pedestrian walkways, which were originally designed to allow pedestrians to cross the bridge even when the bascules were raised. These walkways provide stunning views of London and the Thames, and today they house exhibitions, which makes the bridge not only functional but also culturally significant. The construction of Tower Bridge presented numerous challenges, which required innovative solutions to overcome. The riverbed upon which the foundation was built was muddy and unstable. To rectify this problem, large caissons, which are watertight structures made of timber and steel, were used. These caissons were sunk into the riverbed, and the water was pumped out, allowing workers to excavate and build the foundations in dry conditions. Another challenge was supporting heavy loads. The bridge had to be supported by the weight of the towers and the bascules. Suspension chains and robust piers were used to provide the needed support. The towers were constructed with strong steel frames and granite. Portland stone was also used for added strength and durability. Another challenge was designing a reliable mechanism to lift the bascules and allow ship passage while maintaining roadway functionality. Engineers implemented a state-of-the-art hydraulic system powered by steam engines, which operated large pistons to raise the bascules. This system was later upgraded to an electro-hydraulic system, ensuring continued efficient operation. To ensure that the construction of the bridge did not disrupt the vital river traffic on the Thames, it had to undergo careful planning and scheduling of construction activity. The construction was completed in phases to ensure that at least one channel of the river was always open for ships. The use of stone cladding on the steel framework provided the desired Gothic look while ensuring the bridge's strength and stability. By addressing these challenges with innovative engineering and careful planning, the builders of Tower Bridge were able to create a structure that was both functional and visually iconic, enduring as a symbol of London's architectural and engineering heritage. 3. The Akashi Kaikyo Bridge, based in Japan and also known as the Pearl Bridge, holds the record for the longest central span of any suspension bridge, at 1,991 meters. Completed in 1998, after a decade of work, it was engineered to withstand earthquakes and harsh weather conditions. The need for the bridge arose after a tragic ferry accident in 1955 during a severe storm, which claimed 168 lives. This incident underscored the necessity for a safer and more reliable crossing. The bridge is not only an engineering marvel but also a testament to advanced earthquake and windproof design. Engineers incorporated cutting-edge technology to ensure its resilience against the harsh weather conditions of the region, including the frequent typhoons and seismic activity. With towers standing 282.8 meters high, the bridge's total length reaches 3,911 meters, supported by 300,000 kilometers of steel cables. For the bridge to withstand potential earthquakes, engineers incorporated advanced seismic isolation techniques, including massive bearings and shock absorbers, to allow the bridge to absorb and dissipate seismic energy. This design ensures the bridge can withstand up to magnitude of 8.5 earthquake. The Akashi Strait presents a major challenge. The bridge experiences strong ocean currents and severe weather conditions, including typhoons and high winds. These factors complicated the construction process, particularly in anchoring the bridge's massive towers. To address these challenges, construction teams used caissons and specialized underwater techniques to anchor the bridge's foundations securely. They also implemented robust construction methods to handle the harsh marine environment and incorporated weather-resistant materials. The construction was severely impacted by the 1995 Great Hanshin earthquake, which caused the two towers of the bridge to shift by approximately 1 meter. This delay pushed back the project's completion and increased costs. After the earthquake, engineers had to adjust the bridge's design and construction plans to address the damage. The towers were reinforced, and the project timeline was extended to ensure the bridge met safety and design standards. The bridge's construction required precise engineering to manage the enormous scale and weight of the components, including the massive steel cables and bridge deck. Engineers utilized advanced technologies for measuring and aligning the bridge's components accurately. Special construction techniques, including floating cranes and large-scale prefabrication, facilitated the assembly of the bridge's massive elements. Building a structure of such scale in a busy maritime area raised significant environmental and safety concerns, particularly regarding pollution and the safety of maritime traffic during construction. Measures were taken to minimize environmental impact, including using barges and careful management of construction materials. Safety protocols were strictly enforced to protect both workers and maritime traffic. These challenges, along with natural disasters, highlight the engineering ingenuity and resilience required to complete the Akashi Kaikyo Bridge, making it a landmark achievement in modern civil engineering. The Sydney Harbour Bridge, sometimes known as the Coat Hanger, due to its distinctive arch shape, was completed in 1932 and remains one of Australia's most well-known landmarks. We will delve a little further into some interesting elements of the bridge, including the challenges faced during construction and innovative methods used to construct the bridge. Designed by engineer John Bradfield, the bridge was built to connect Sydney's central business district with the northern suburbs, addressing the growing transportation needs of the city. Construction began in 1923 amid the Great Depression, a period of economic hardship. The bridge's development was crucial for boosting employment and supporting economic recovery. The Sydney Harbour Bridge is a vital piece of infrastructure, significantly improving transportation across the harbour and fostering urban growth. It has become a symbol of Sydney's progress and resilience, often featured in celebrations like New Year's Eve fireworks and national events. The bridge features a massive steel arch that spans 503 metres across Sydney Harbour, making it one of the world's largest steel arches. The arch is supported by massive concrete and steel pylons at either end. The arch design allows for the long span needed to cross the wide harbour, providing structural stability and allowing for the bridge's road and rail components to be positioned below it. Remember to sign up for our newsletter below to stay up to date. The bridge uses approximately 53,000 tons of steel, which was fabricated in the United Kingdom and shipped to Australia. The steel was treated with a special anti-corrosion paint to withstand the harsh marine environment. The steel was assembled using innovative techniques of the time, including the use of cantilevering methods to build out from both sides of the harbour and meet in the middle. The bridge employs a catenary cable system, which distributes the load evenly across the arch. This system helps manage the forces acting on the bridge, allowing it to support both vehicular and rail traffic. The catenary design ensures that the bridge can handle dynamic loads, such as those from heavy vehicles and trains, while maintaining its structural integrity. To construct the bridge, engineers used a method where sections of the bridge were built outwards from each side until they met in the center. The cantilever method allowed for the bridge to be assembled without scaffolding in the water, minimizing disruption to maritime traffic and reducing construction risks. The bridge's pylons, which rise 89 meters above the harbor, are made of reinforced concrete and steel. They were built using a combination of traditional and modern techniques to ensure strength and stability. The pylons feature a classic Art Deco design, blending functional engineering with aesthetic appeal. They provide essential support for the bridge's arch and contribute to its iconic appearance. The bridge includes pathways and access points for maintenance, allowing for regular inspections and repairs. The design incorporates safety features such as ladders and walkways for maintenance crews. The bridge's design considers long-term upkeep, ensuring that it remains operational and safe for decades. Construction process and obstacles faced. The construction of the Sydney Harbour Bridge faced several significant obstacles, which required innovative solutions and perseverance to overcome. Obstacle: the bridge was built over a busy harbour, requiring construction to be carried out in a challenging marine environment with strong tides and fluctuating weather conditions. Solution: engineers employed innovative construction methods such as cantilevering sections of the bridge from both sides of the harbour, which minimized disruption to maritime traffic. Temporary platforms and safety measures were used to manage the challenging conditions. The construction involved working at great heights and in hazardous conditions, leading to concerns about worker safety. Aligning and connecting the bridge's massive steel sections, especially those built on either side of the harbour, presented significant technical difficulties. Engineers employed precise measurement and alignment techniques. The use of hydraulic jacks and other advanced tools of the time facilitated the accurate assembly of the bridge's components. The construction impacted the local marine environment and required careful management to minimize pollution and disruption to the harbour. Environmental regulations were followed, and construction practices were designed to mitigate pollution. The project also included provisions for the ongoing maintenance of the surrounding area to address environmental concerns. Please give this video a thumbs up, share it with your friends, and subscribe for more fascinating stories from the world of engineering.